It's rare when someone picks up your product and wonders how it was made. Understanding how a design was taken through to manufacture, and uncovering the effort and the innovation required to turn raw materials into a finished product. It's not easy to do what you do, but that's where Autodesk Fusion 360 can help. Our tools enable you to move faster, supply better products, and change the world by giving you a single solution to design, validate, manufacture, and share your vision with the world. In addition to the core design, simulation, and manufacturing capabilities of Fusion 360, Fusion 360 for Manufacturing goes further, providing professional-grade advanced manufacturing tools and capabilities with a range of benefits to help you take your business to a whole new level. Fusion 360 for Manufacturing includes access to 3D design and modeling tools that are manufacturing aware to simplify and speed up your product development process. And when your design is done, you can then choose the best method for manufacture. Apply automated whole part machining strategies with optimized passes which cater for variable geometry. Modify toolpaths to delete segments or move start points without the need for recalculation. Recognize holes automatically, even in multi-axis, and utilize machine tool probes to quickly set up your parts and verify them with surface inspection to improve part quality. Unlock additional CAM programming tools to maximize your CNC machine usage with 3+2 and 4 and 5 axis simultaneous machining strategies. Access automated workflows for additive manufacturing of metal parts with intelligent print orientation and associative support structures to increase printed part accuracy. Utilize advanced nesting and fabrication capabilities to create optimized and associative multi-sheet layouts for sheet metal and non-sheet metal parts ready for cutting on your CNC machines. And easily access and manage the data that flows through the business, regardless of whether you're in the design office, on the shop floor, or part of an extended team. Cope with design changes at any stage of production using pre-built workflows with complete visibility and digital approval records, letting you focus on innovation, not admin, enabling critical business decisions to be made rapidly to help complete projects on time and deliver higher value to your customers. In the end, taking a design through to manufacture is complicated, but you can do it seamlessly with Fusion 360. It's rare when someone picks up your product and wonders how it was made. Understanding how a design was taken through to manufacture, and uncovering the effort and the innovation required to turn raw materials into a finished product. It's not easy to do what you do, but that's where Autodesk Fusion 360 can help.
We'll first talk about the static design work. So in the turbo housing that is being designed in this instance, the outer shape of the product from the top view is defined in 2 dimensions. And as we go along, we start creating the nice little curves and shapes and straight lines, arcs, whatever it is we need to do in the 2-dimensional space. You start installing all of that. You start putting in all of the dimensions that you require. You then, in addition, sort of have to understand how the layering of the object works as well. So if you look at an object from the top view, you need to understand what is hidden behind the top view. So then you can start adding your dotted and dashed lines in order for the hidden views to be shown as well. In addition to that, then you also need to envisage in your head what the product looks like from all 3 dimensions, all 3 angles. And you need to now put that into the 2D drawing space manually, and that can be achieved by using construction lines, drawing from sort of the flange ends. So in order for you to have the ability to have the right dimensions on the side view as well as the top view and the front view. Now in 3 dimensions, what you see in your mind, you need to put on a 2D flat space, and using the dimensions as well as the nodes. Of course, in 2 dimensions, you are modeling at full size. The only difference is that you can you would need to then pull your center lines, and in order for you to be able to match everything, take all of those lines across and update your views. And those views again will have different dimensions, of course. And I'll bring us back to the point of the requirement for us to envisage it in our minds and be able to put measurements on it, and we do that step by step on each component and aspect of the design that you're putting together. This is a bit of a time-consuming process, and of course it uses a lot of manual work, and that brings us to the situation of the ability that's available, the expertise that we have available in South Africa and otherwise, to be able to envisage these things and then put them down on paper. It's all well and good to have a pretty design on a screen, but the collaboration aspect of it has to come into play as well. It's nice to have that image where you put the drawing together, you've modeled everything quite neatly, everything is correct as per your requirements. Once all of that is put in place, I mean, sending a floating drawing randomly doesn't really mean much until you've actually added your information. So which project is it? For whom is it? Is it to give it a reasonable name? All of that requires a title block. A title block having the information of who the designer is, who the engineer is, who the manufacturer is, even, and whether or not the drawing gets approved or not. All of those sort of aspects need to be added there as well. Now, in AutoCAD, what you would do is you would create a title block manually with the process of creating a rectangle and then adding your slots for everything, using updating fields, and then typing everything in, one at a time. And if you have the situation where you want to also collaborate outside of your own organization, then you would also need to put your organizational logo on the title block and on the page that's being transferred. Now, everybody needs to know whose work this is. Everybody needs to know whose intellectual property this is. That intellectual property is also being managed by having your name on the drawing at all times. And it always allows you to collaborate a little bit further by sending it into a PDF or a two-dimensional DWG DXF. Whatever the case may be, that information, it starts to become a little bit more and more critical as you go along, because as the design progresses, it also needs to be taken to manufacturing. For the designer to be able to transmit information, that information needs to be put on the page that's being sent out as well. So once your title block has been created, you've put your nice little logo in, you've got all the data that's been filled in, your who the engineer is, date of creation, the IP information, who's approving it, all of that information that's needed for controlling of the drawing and for your audit purposes, revision control, all of that stuff has to happen in this particular drawing page. And in that drawing page, along with all of that, is machining notes. Now, machining notes will be added, one by one, individually. In an individual process, unless every single one of your processes is exactly identical. Now, do you want to have a rough surface finish? Do you want to have a smooth surface finish? Do you want to have a specific type of finish? What type of welding are you doing? What type of fastening are you doing? All of those fastener types, any and all notes that need to be sent to your manufacturing team and to anybody else that needs to know what the manufacturing of this product entails, as well as the fitment of thereof. Now, again, we would also have to add material sizes, material types, your masses, what sizes, what your inner holes need to look like. Is it being casted? Is it being milled? All of that information has to go on the drawing as well, and that also takes a large amount of time where the designer themselves or the engineer needs to start adding the notes manually, one by one, and that also increases the possibility for mistakes.
And now this brings us to dynamic design. Is there a cheaper, better, faster, more efficient way of creating drawings from our designs and communicating this with the manufacturing team? What are some common misconceptions around a dynamic 3D workflow? Firstly, that it's difficult to learn, that it's far too complicated for the average draft person to learn how to use. Secondly, that it's too expensive to purchase and to use. There are many competitive programs that have very high running costs and high initial license purchases. And thirdly, that it's too fancy. We just need 2D drawings. What is Autodesk Fusion? It's more than just CAD. It's the future of design and manufacture. It includes an integrated CAD/CAM solution. It includes simulation, generative design, you to create fully fledged working drawings. We'll now demonstrate how to move from a 2D sketch to 3D geometry. Firstly, we specify which work plane we want to create the sketch in. Here we will be creating a spiral with which we will create our 3D geometry. We can parametrically input the values of our spiral dimensions. This drawing workspace, you will see, is very similar to your standard 2D CAD package. Here we're using a regular line drawing tool to create the outlet of our exhaust pipe. We can simply click to draw the lines, and here we'll use a fillet tool to create the curve. Once we've finished the sketch, we can create extra construction planes where we will define the cross-section of our exhaust. This tool allows us to create a construction plane perpendicular to the curve that we have just created. Once we've specified the location of the construction plane, we can then create a new sketch upon which we can draw the cross-section of our tube. We can input the exact diameter of that sketch. We see that it turns black to show that it is fully constrained. And we continue to repeat the process to create the final diameter of our tube. See that our sketch is fully defined and we are ready to create 3D geometry. In order to create the 3D geometry from our 2D sketch, we can use a function called loft. This allows us to create a 3D shape that flows from one cross-section to the other and sweeps it along the center line of our spiral curve. We have different functions that our 3D geometry can. There are different functions that the 3D geometry has. We can cut a body, or we can create a new body. Here we've created a new body, and we see that with a few clicks we've created this 3D tube. We can repeat the command to create the outlet of our exhaust. And there we have our 3D geometry. And now we can see how quick and easy it is to make changes to the 3D geometry. To make changes to our 3D geometry just by editing the sketch. We can go into the sketch and type in the new dimension that we would like for the outlet. Again, we want to change the diameter of the end of the pipe. We just go into the sketch, change the dimensions, and the 3D shape is automatically updated. We can fillet our 3D geometry. Now, we would like to pattern this shape numerous times. We don't have to redraw the shape, and we can pattern both features of our extrusion as well as the fillet that we created. Select these features from the timeline, select the axis of our array, and input the number of times we would like to repeat this shape. We can continue to add more detail to our form. We can add a fillet along this top edge. You can use the chamfer tool to create a chamfer along all of our sharp edges. And you can see that each operation appears on the timeline, and you can roll back to it to make changes at a later stage. We can also create 3D geometry that will be used to cut our existing 3D geometry. We'll draw a new circle that defines the housing. We can use the extrude tool to then extrude a shape that will be subtracted from our existing geometry. We can select a symmetrical extrusion that will allow us to extrude the same distance on the top and the bottom of our construction plane. We can see how the view dynamically updates to show the changes that have been made and the subtraction that has been done to the shape. We can then go back and show the sketch again and use the same circle that we've drawn to create the solid body of the housing. We can choose the function to add to join this new geometry to our existing geometry. So what's next? Making the design a reality. We want to create a physical product from our design. So now we can look at the CNC machining component of Fusion. We can create a setup and we can choose the solid model as our stock, since this is a cast part that we will be machining. Fusion offers fully modeled 3D models of various CNC machines to give us a nice simulation of exactly how the machine is going to move as it machines this part. There's a huge selection of preloaded CNC machines that come with Fusion. We'll start with some basic 2D operations. We'll choose a face operation from the drop-down list. We'll select our tool. We'll select our machining area. And with the preset settings, we'll see that we have our facing toolpath automatically generated. We can do a quick simulation of this to see that we're happy with the toolpath movement. We can then move on to a drilling operation. We can quickly inspect the holes to see what diameter tool we need. We can go and select that tool. Fusion already has a preloaded list of tools of different diameters. Select the correct tool for these holes. And select our hole geometry, which will automatically tell us the top and the bottom depth of the hole. Go to our 3D model of the CNC machine, and we can quickly watch a simulation of those toolpaths. We can now continue on to the next step of our machining. We will choose a 2D profile, choose an appropriate tool, and then select the outer edge of the flange in order to machine that edge. We will then select a bore operation to mill the face of that inside bore. Again, selecting the appropriate tool. And we can work with the preset settings of the machining operation. We'll now take a look at Fusion's impressive selection of simultaneous 5-axis machining operations. We can choose from the 3D machining operations, which are model aware and will allow us to machine our 3D model with very little geometry selection. Here we'll select the faces we would like to machine. And it will gather all of the data from these surfaces rather than having to input any depths or heights. We will preview what this toolpath looks like if we just use 3-axis machining. And if we were to simulate this, we'll see that eventually our tool holder collides with the piece. So we need a different machining strategy for this in order to eliminate those collisions. We can go and edit the toolpath, and we can change our operation type from 3-axis to 5-axis, and we can turn on collision detection. This will use our 3D model to tell the machine how to tilt and turn in order to machine those surfaces without any collisions. We can see the toolpath is extended all the way to cover all of our surfaces, including the undercut areas. We can now run the simulation with our machine model to see that we no longer have any collisions. As the tool holder nears the part, we see it starts activating those 5 axes to tilt the part in order to cut it correctly. And having these machine simulations really allows you to fully exploit the capabilities of your machine with very little risk that you'll have any kind of collisions when you are finally running the program on your part. Very easily navigate the view to watch closely to see what the machine is going to do. That is an overview of the basic features and some of the advanced features provided by Fusion, allowing you to work in a dynamic 3D workflow that takes you all the way from design conceptualization to producing your machine G-code in one single software package.
So let's talk a little bit about the key takeaways from this session. So I spent the majority of the first part of this session talking about the drawbacks of static modeling. There is, however, a two-dimensional drawing has a very big role to play still going forward. Think electrical diagrams, wiring diagrams, things that can be done manually. And in some cases, if you just want a quick top view of something, it's much easier for the user, the operator, to be able to just quickly plot together something in 2 dimensions and send it off for a quick visual. And the main thing is that this is a manual and static process. So we are assuming a larger level of skill in order for the manual inputs to take place correctly. And then the machine operator leads the process of how the manufacturing is taking place. So you're sending them a flat plain drawing with very little intelligence. That intelligence level from the 3D aspect of things will send through like your NC codes, like has already been mentioned. The NC codes, your automations when it comes to machining, all the information that comes through in terms of casting sizes, billet sizes, all of that can be sort of portrayed in 3 dimensions without fully cluttering your drawing with a whole bunch of drawing notes. And considering that all the technical communications are via the drawings get sent out to manufacturing or to the outsourced manufacturing, internal manufacturing, whether it's the customer. So they don't understand 100% exactly what the intent is without all of that information. And is it easy? How easy is it to actually transfer all of that information onto a piece of paper? And how easy is it to interpret that information once the piece of paper gets to the endpoint? That is a large portion of where the 2D comes a little bit awry. And from that point onwards, you kind of understand where three-dimensional or dynamic modeling is much simpler. It's intuitive. You can see the model as you're modeling it. You don't have to imagine it and then draw it flat. It's far more the automation level that I just spoke about as well, where you're able to send out all of the information that you need contained within the model itself. And from the 3D drawings, the 2D model, 3D drawing can then be very, very easily generated with a click of a couple of buttons. So yes, there is a definite benefit to using 3D depending on the space that you're working in. In terms of your manufacturing industry, it does make a lot of sense. However, there is, as I said, a large amount of large role that 2D still can play, considering the type of drawings that we do. So once again, your PNIDs and your electrical diagrams and all of those sort of things are all in 2 dimensions anyway. So, I mean, there's not really much of a sense in trying to force that to go into 3 dimensions. I hope you enjoyed this. Have a lovely day further.